All right, Unit 9, Application of Thermodynamics. We're on question number 31, so let's get to the questions. And right when we get to 31, we see that it's a repeat of question 30. So go ahead and go back to number 30 to see how to answer that question. Let's start at 32. All right, so you have some element M plus Ag yields that and that. According to the information in the standard reduction potential for the half energy of that. Okay, so this Ag is reducing, yeah? This Ag is reducing. And that Ag is reducing. Now, don't care about the 3 moles. We don't care about the coefficients when we're dealing. We do care about it in K equilibrium. We do care about it in Hess's law, but we don't care about it with E cell. All right, so they're both reducing. We keep that the same. Now, since they're reducing, that this Ag plus is gaining an electron to become Ag. Just like this Ag plus is gaining an electron to become Ag. So we know right now that this is our rig. They're gaining electrons. This is our cathode. Okay, so M. Check out what M's doing. M is neutral, no charge, becoming 3 plus charge. It must be losing its electrons because it's becoming positive. So therefore, M is oiling. Okay? It is our anode. So the E cell is equal to the E cat minus the E an. Now, the E cat we know is 0.80. The E cell overall is 2.46. So how do we calculate for the E anode? Okay. To get the E anode, we're going to have to do 0.80 minus 2.46. Yeah. 0.80 minus 2.46 is 0.166, and honestly, you just know that it's sorry. No, it's not. 1.66. Okay, you know the number is going to be like it, and it's going to be negative 1.66. You know it's going to be negative, and you also know that it's going to be over 1. So the answer had to be A. Okay, that's a pretty straightforward question. A little bit different than we've seen before, but still on the same topic of E cell. By the way, you notice that your E cell is positive. If your E cell is positive, this must be an electrolytic cell happening here. This is not spontaneous. All right, here we go. Ooh, look at this. Diagram shows an experimental setup to use to an electroplate a small object. Current of 0.80 amperes is supplied here. Okay. Whoa. Okay, this is going to be a lot of work. Okay. And 30 minutes, which of the following equations can be used to calculate the approximate mass? All right, I want to remind you something. Faraday's constant, 96,485 coulombs per second, okay? Oh, no. That's not coulombs per second. Yeah, that's coulombs per moles of electrons. And an ampere is also equal to a coulomb per second. Okay, so those are some of the things that you're going to need. All right, let's see what you do. You start with what you have. You have 0.80 amperes, which is coulombs per second. And the other thing that I want you to see is that you're trying to get to grams, okay? So, okay, 0.8 coulombs per second. All right, well, we have 30 minutes, so there's 60 seconds in 1 minute. There's 30 minutes that we have, so that's going to get rid of our time by being able to cancel out all these. That was given in the question, right? So, not the 60, just the seconds. Those units are going to go away. Now we can take care of the coulomb. Now the coulombs we can take care of using Faraday's constant, 96,485 coulombs per 1 second. Or sorry, jeez, I keep doing that. That's amperes I keep thinking of. 1 mole of electrons. And the substance that we're using is Ag, and Ag only gives out 1 mole of electrons, right? So that's kind of nice. Okay, we're gonna have to extend this. There's one mole of electrons per 1 mole of Ag. And I know I should write Ag plus there, but it's not that big of a deal. And then 1 mole of Ag is equal to 107.9 grams of Ag. I think that's the molar mass. So looking at this, I have 0.8 times 30 times 60 divided by 96,000 times 107. Okay, so the correct answer is C. 0.8, 30, 60, 107.9 divided by that. Okay, that's like one of the longest dimensional analysis problems, and you get those when you do these electroplating ones. But it's just, dude, it's just about getting to your like your dimensional analysis, getting to the mass here, and to get there, you just need to know these two things. Faraday's constant is 96,485 coulombs per mole of electrons, and amperes are coulombs per second. That'll help you a whole lot to do this. All right, number 34. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Nothing happened. 1, 2, 3, 4, 5. Ooh, everything happened. No catalyst with a catalyst. What does a catalyst do? Well, if the reaction was something like this, now it became lower activation energy. So K is equal to 2.2 times 10 to the 4, which is a very big number, meaning that there should be more products than reactants, but it wasn't happening without the catalyst. The Ka is a stoichiometric mixture of CO and H2 was allowed to react in 2 different 2-liter rigid containers at a constant temperature of 298. The reaction is represented by the equation above. Diagram 1 represents the uncatalyzed reaction, and diagram 2 represents the catalyzed reaction 1 hour after the reactions were mixed. Which of the following correctly explains the experimental results represented in the particle diagrams? Well, if you look at the pictures, you see that the one without the catalyst, the products aren't producing, but with the one with the catalyst, the products are. What is it's the activation energy that's holding this from getting where it needs to go. So we know that the delta G is negative. Why? Because if the K is greater than 1, you have a lot of products, very little reactants. That means your delta G is really negative. It's really negative. You really have a reaction that's going to happen spontaneously. Now, here's what you're going to argue. You're going to say, wait, if we have to use a catalyst, then how is this a spontaneous reaction? No. Look, if your delta G is positive, it's not going to happen at all, okay? A delta G that's negative, it'll happen. It'll just happen really, really slow. Look, water and iron are a spontaneous reaction, but to form rust. But that doesn't happen overnight. It happens very slowly. A catalyst just helps it happen faster, okay? So the correct answer, I'd love to read through all these with you, but let's just say it's B. Although the reaction is thermodynamically favorable because delta G is negative, okay? So you could have already canceled out C and D because they don't say delta G is negative. Based on the K value, only the catalyzed reaction could proceed in 1 hour because it had a lower activation energy. Notice that they say that only the catalyzed reaction could proceed in 1 hour. The other one would have happened. It just would have taken a lot longer than 1 hour, okay? All right. Number 35, you have a galvanic cell. This galvanic cell is going to have a voltage of 3.17. How do I know this is a galvanic cell? 1, there is no outside source of power. 2, there is a salt bridge. Okay, that salt bridge is key here. So, the galvanic cell, and it says, the first thing it says in the question is, the galvanic cell. Okay, that's how I knew. The galvanic cell shown above generates a cell potential of 3.17 when operating. Oh, this one is hard. You know what? Before we do number 35, let's do number 36 because I think it'll help like warm us up to number 35. Okay, number 36 says this: Cu 2 plus becomes Cu. Mg because Mg2 plus. So you have your oxidation and your rig, right? Your Mg is oxidizing, your Cu is rigging. Your E cell is positive. If your E cell is positive, that means your delta G is negative, meaning it is thermodynamically favored. A galvanic cell generates a potential of 2.71 volts when Cu is equal to Mg, 1, The chemical reaction represented above, which of the following provides the best justification that the given conditions can be used to decrease the cell potential, that you can get E cell to be less than 2.71? Okay, well, oh, this is super interesting. Okay, so if your Cu is equal to 0.1 and your Mg is equal to 0.1, oh, do you see that? Dude, this is tricky. Okay, if your Cu and your Mg are equal, okay, if your Cu and your Mg are equal, then think about your products over your reactants, okay? Your products over your reactants, your K would be equal to 1. That means your lnK, your delta G is equal to negative rat link. In this scenario, your products and your reactants are equal. That means your lnK is equal to 0. Okay, meaning your delta G is neither thermodynamically favorable or not thermodynamically favorable. Okay, well, okay, if you have your Cu, B is the same way. If they're both equal to each other, then your lnK, your K is 1. Therefore your lnK is also equal to 0. Okay, so this is neither thermodynamically favorable or thermodynamically unfavorable. Your delta G is neither positive nor negative. Your delta G is 0. All right, then you have this scenario where your reactance is greater than your product. See, Mg is a product, Cu is a reactant. If your reactants are greater than your products, then you're going to have a K that is less than 1. It's going to be a fraction. Your denominator is going to be bigger. And so what will your lnK be? Then that means when your K is less than 1, your K is negative. Your lnK is negative. If your lnK is negative, then you have a negative, which makes a positive delta G. You are not spontaneous. If you are not spontaneous, your E cell would be less, would not be, your E cell would not be positive. Your E cell would be negative. Okay? So the correct answer here is D. Think about all the things that have to happen for D to be true. Okay? So you have more product, Mg2 plus, than you do reactant. If you have more product than reactant, then it means your K is greater than 1. If your K is greater than 1, then your ln of K is a positive number. So you have a negative times a positive times a positive times a positive, making delta G negative. That would make it spontaneous. If your delta G, so by choosing the answer that had more product than reactant, okay, then you have a negative delta G. If you have a negative delta G, think about it in terms of this equation. If you have a negative delta G, you have a negative times a positive times a positive. E cell must be positive, which is what we're saying. E cell was positive. So for E cell to be positive, we must have more product than reactant. The correct answer is D. All right, number 37. Consider the reaction represented above at 298 K when equal volumes of N2 and H2 each at 1 ATM are mixed at a closed container. No formation of NH3 is observed. No formation is observed. We can't see it. But, you want to say, oh, this is a not spontaneous reaction. Hold on. Delta G is negative. If delta G is negative, then it is a spontaneous reaction. It doesn't require help. But if your delta G is negative, why can't we observe it? Well, I don't know about you. I've never observed rust form on iron. Okay, rust forming on iron is a spontaneous reaction. It just takes really, really, really long because it has a high activation energy required. that might be the case here. Look, we should be glad that this, even though this is a spontaneous reaction, it doesn't happen a whole lot. That'd be because that would be like a bunch of nitrogen gas and hydrogen gas forming ammonia all the time. You know how much nitrogen gas and hydrogen gas are in our environment? Like, if you have a bunch of, like, anytime we let out hydrogen gas, we just have a bunch of ammonia raining down on us. You know, I mean, maybe crops would grow really fast, but anyway. All right. The answer, is B. The high activation energy makes the forward reaction super slow. I mean, it's not that it is going to happen. It's going to happen. It's just going to happen super slow, which, you know, it doesn't mean it's not spontaneous. It is spontaneous. It's just high activation energy. All right, 38. Oh, here we go. This is confusing a little bit. You know why? I think it's an electrolytic cell. You know why I think it's an electrolytic cell? There is no salt bridge. However, where's the power supply? Electrolytic cells are supposed to have an outside power supply. I think we got a question here. The decomposition from NaCl into Na and Cl2 is thermodynamically unfavorable. Yes, it isn't. You know what? The delta G is positive. Why is the delta G positive? Because the E cell is negative. And why is the E cell negative? Because it's an electrolytic cell. Oh, that makes sense. If it's thermodynamically unfavorable, that means it happens. It cannot happen. It needs help to happen. And where's that help? Where's that power supply? It's not here. The decomposition requires an input of energy from an external source. That's what I'm talking about. The diagram represents an electrolytic cell that can be used to drive the decomposition reaction. Which of the following identifies a flaw? A flaw. We've been talking about this from the beginning. What's the flaw in the representation? Where's your external source of energy? This is an electrolytic cell. I demand that there be power being put into this, or this will not happen. It won't. 38. All right. Ooh. Okay, this is 39. You got hydrogen this is a good question. Hydrogen peroxide, and you got to remember your oxidation number questions, okay? Hydrogen peroxide has an E of that. Your oxygen plus H pluses has an E of that. So what is the oxygen of the whole thing? What is the standard reduction potential for the half reaction represented above? They're saying, what's this? Okay, what's that? All right, here's the thing. We're gonna keep this on this side, right? I shouldn't use, you know what? We're going to keep, you know what I'm going to do? I'm going to make this bigger. Okay, we're going to keep this on this side, right? But we're going to need to cancel out. We're going to need to put this H2O2 onto the other side. Now, if we keep this first reaction the way it is, this is showing that electrons are on the reactant side. So this is rigging, right? Electrons need to be gained for this E cell to occur. But on the other side, this one needs to be flipped, but I don't see electrons here. But you know what? Do your oxidation numbers. If you remember, H is always +1 unless it's, you know, on the other side. But oxygen's always -2. However, and over here it's 0. But this oxygen here is a -1. Do you guys remember that? The oxygens over here are actually, becoming, oxygens in a peroxide have a oxidation number of -1. So here, if you see it, the oxygens, that oxygen right here, -1 to 0, it is losing electrons. It's becoming positive here. So if this is losing, it is oiling here. This is our oil, that's our rig. This is our anode, this is our cathode. Look at the oxygens here. The oxygen here is a 0 charge becoming a -2 charge, so that is gaining electrons. Yeah, it's rigging like we thought it was. Okay, so there's our anode, there's our cathode. So our E cell is our E cat minus E an, which is 0.55. Your delta H, or your E cell is going to be C. It's going to be positive, and that should tell you that this is an electrolytic cell. It should tell you that delta G is not spontaneous. It should tell you that K is less than 1 because there's more reactant than product. I mean, there's so many things that need to be like clicking on your brain when you see like that number. You'll get there. Promise. Actually, I don't know who I'm talking to, so I promise nothing. Okay, which of the following is true for the decomposition of H2O2? Is it? Am I supposed to use this information? Doesn't say. I guess this is the decomposition of H2O2? No. Okay. I'm gonna assume that the E cell of this, okay, that we just did, we found out the E cell was positive 6.8. The opposite would be the E cell would equal negative 0.68. In other words, okay, I don't know that it actually equals negative 6.8, but I do know that it is the opposite sign of this because it would be going the opposite direction. If going the forward way required energy, the backward way would be natural, right? So the E cell is negative here. Well, if your E cell, wait, am I totally wrong with what I just said? Oh yeah. Okay, I totally screwed up that last one. This is the E cell. This is the decomposition. Okay, the last one. The last question I just did, 39, I got the answer correct, but I said everything backwards because I don't know. I don't know why it was wrong with me. The last question, E cell turned out to be positive. So since E cell turned out to be positive, delta G was negative, making it spontaneous, meaning that there was the K was greater than 1 and you had more products than reactants. My apologies. I'm sure people just exploded in anger, but you know, you're going to tell me I'm wrong, keeping track and tallying my score. But okay, I would say that this is the decomposition of hydrogen peroxide that we're talking about. And see, the E cell of the decomposition of hydrogen peroxide is positive. So, okay. So our E, okay, let's explain this, just so I don't get a lot of people confused. Delta G is equal to negative NFE, right? But delta G is also equal to negative RT-ln-K. Now, so these two can be equal to each other because they're both equal to delta G, right? So let's get this out of there, okay? Now, this is a positive number. Oh, I'll make that smaller. This is a positive number. That's a positive number. This is a positive number. This is a positive number. The negative and negative cancel out. So really, you're just wondering what's E compared to ln-K. Okay? So if E is positive, then your ln-K needs to be positive as well, yeah? How do you get ln-K to be positive? Well, that means your ln has to be a K, or your K has to be greater than 1. If your K is greater than 1, if your K is greater than 1, ln-K will be a positive number. If it's less than 1, meaning you have more reactant than product. So if your E is positive, your K is positive. So it won't be this one, won't be this one, and it won't be this one. But if your K is positive and your E is positive, that means your delta G is spontaneous, therefore it can't be that one. The answer is C. All right, of the following reactions, which involves the largest decrease in entropy? Okay, let's do grandparents and grandkids again. All right, we have a grandparent becoming a grandparent with a grandkid. Okay, that is increasing in entropy. The disorder is nuts. That grandkid just destroyed their house, okay? Now you have 2 grandkids. No, you have a third you have 3 grandkids on the left side. Now you only have 2 grandkids. Okay, it got much calmer. Okay. Ooh, that decreased in entropy. But it says largest decrease. All right, now you have a grandparent and 2 more grandparents. So you have 3 grandparents. No, you have, 3 grandparents becoming 1 grandparent and 2 more grandparents. What? So you have 3 grandparents becoming 3 different grandparents. No, that's no change in entropy. The entropy is the same. You have a grandkid plus 5 grandkids, yielding 3 grandkids and 4 grandkids. So in other words, you have 6 grandkids becoming 7 grandkids. There's more disorder there. Your entropy has increased. Looks like B is our winner, but let's check last one. You have 4 grandparents and 3 grandkids. Now you only have 2 grandparents. Ooh, that calmed down a whole lot. You had 3 grandkids there, man. And you had an extra grandparent, right? More things to run into. The correct answer, the largest decrease, is E, okay? Yes, B decreased, but it was 3 grandkids becoming 2 grandkids. That's still chaos, okay? 3 grandkids to no grandkids? Oh, yeah. E, yeah. That's the answer. All right. Let's take a look at this. Delta S. It asks us to find the delta S for the reaction, and to find the delta S for the reaction is a very simple formula. You're going to go delta S is equal to S final minus S initial, or S products minus S reactants. Okay, so this is going to become, all right, 2 AgCls, which is 2 times 96, and then you're going to have 1 CaNO3, which is 240, and then you got to get, that's your products, and then you have to minus your reactants. Your reactants are 2 AgNO3s, 220, plus 60, so that's yeah. Okay, I would normally tell you to just estimate this and calculate it, but you know what? You look at the answers, these are really close. Like these values, I don't like them. Dude, calculate this one, okay? All right, work it out. This is 192 plus 240. This is 440 plus 60. This is 500 on this side. This is 432 on this side. The answer is 68. Or it's negative 68. The answer is A. And we're doing good. We're doing good. That delta S is entropy of the products minus entropy of the reactants. Okay, we're doing all right here. Number 43. Which of the following particle diagrams represents a process during which the entropy of the system increases? Entropy of the system increases. Okay. These are a bunch of grandparents that became a bunch of grandkids, right? Crazy! The answer is A, okay? Look, more disorder, more chaos. Less disorder, less chaos. This is less disorder. There's 6 moles of gas. There's only 4 moles of gas. This is 6 moles of gas becoming 3 moles of gas. These are all decreasing in disorder. Less chaos. This is more chaos. Answer is A. 44. This was like weird for me to think about. I didn't like this question. Okay, quantity that would be 0 for pure perfect crystal at 0K, and then it says activation energy. What? What does a pure perfect crystal have activation energy? You only have activation energy when you have reactions. When you have reactions, because you need a reactant and a product. A pure perfect crystal doesn't have a reaction, so that doesn't even exist. Okay, enthalpy of formation. What? How do you have enthalpy? How do you have enthalpy? What? No. Okay. Now entropy. Yeah, that makes sense because you would have 0. Like, okay, A and B. It's not that you have 0 activation energy or 0 enthalpy. You don't have activation energy and you don't have enthalpy when you have something that is by itself. Like that doesn't exist. Now entropy would be at 0. There is no entropy for a pure perfect crystal because entropy can only be measured by its change, right? So the answer is C. But I just thought that was a weird question overall. I didn't like it. Not cool. I don't know. Don't ask me weird questions like that. That's not enough sentences to be a question. on the AP exam. Okay. Number 45. All right, now this is what I'm talking about. This is AP, look at all these words. Okay, the reaction of iron with oxygen. Hey, how many times have I used this example? But I kept saying water, but it is really, the water is just a way of getting that oxygen there. The reaction of iron with oxygen to form rust is represented by the equation shown above. A student cleans 2 iron nails and places each in a capped nail in a capped test tube. The following table gives the experimental conditions of the student's observation after 1 week at room temperature. Test tube 1, dry air, no visible rust on the nail. Air and water, rust spent in the water and on the nail. Okay. The student claims that the formation of rust in test tube 2 shows that the reaction is thermodynamically favored. Which of the following justifications should the student use to explain why rust did not form in test tube 1? I see. A, the reaction does not occur at an observable rate when water is not present because it proceeds through a mechanism with a high activation energy. Water is the catalyst that allows oxygen and iron to react. Okay, I've been saying water and I keep saying water and this, but okay, we know it's thermodynamically favorable because delta G is negative, but what is the water doing? It is helping. So if you have a piece of iron sitting outside your house that's not wet, it will eventually rust on its own. It just will take a really long time. Now, when you get it wet, it'll start rusting. And that's because water is acting as a catalyst. The correct answer is A. The reaction does not occur at an observable rate when water is not present because it proceeds through a mechanism with a high activation energy because water is the catalyst of that reaction.